Friends, welcome to follow up. Let's have a look at problem 1921. Eliminate maximum number of monsters. This problem is yesterday's daily challenge problem. We are going to explain a solution based on the following strategy. So we are going to count how many monsters we can eliminate from the interval. This is a left close and right open interval. So from the current running time to the nearest monster's arrival time, and then we're going to do the summation. So our plan will be the following. First, we are going to digest the problem requirements, and then we look at the logic, and finally we share the code. So this problem is tricky in the sense that we need to count the time besides the number of monsters we can eliminate. So with that said, let's look at the problem requirement. So here we are playing a video game where we are defending our city from a group of n monsters. So we are given a zero-indexed integer array called distance of size n, where distance I is the initial distance in kilometers of the ith monster from the city. And the monsters walk towards the city at a given constant speed. The speed of each monster is given in an integer array called speed of the same size, where speed I is the speed of the ith monster in kilometers per minute. So we have a weapon that, once fully charged, we can eliminate a single monster in each minute, right? However, the weapon takes 1 minute to charge. So the weapon is fully charged at the very start. So we will lose when any monster reaches our city. If a monster reaches the city at the exact moment the weapon is fully charged, it also counts as a loss, and the game ends before we can use our weapon. So we want to find the maximum number of monsters that we can eliminate before we lose, or just the end if we can eliminate all the monsters before they reach our city. So actually this n is sort of dummy because that we just need to count how many monsters we can eliminate, right? So for sure the number would be less than or equal to n because we have in total n monsters. So here are 3 examples. So we're going to look at the first one first. So here the speed are the same, right? Both are 1. So monster 1 will arrive at minute 1, and the monster with distance 3 will arrive in minute 3, and 4 will remain at minute 4, right? So we can first, at time 0, we eliminate the one who will arrive at minute 1. So then at minute 2, we eliminate the second monster. At minute 3, we can eliminate the third monster. So in total, we return 3. This is also the length of this, also the total number of monsters. So in example 2, I guess the purpose of this example is to show at the same time there are multiple monsters can arrive. For example, at minute 1, so 2 monsters with distance 1 can arrive, but we can only eliminate 1, and then we lost the game. So we return 1 in this example. In the second example, in third example, which basically tells us that we need to consider the speed as distance together. For example, in the first 2 monsters with distance 3 and 2, so their speed are 5 and 3. So within 1 minute, both can arrive. So we can only eliminate 1. So that's why we return 1 for this one. And then the monster with distance 4 arrive at minute 2, but at that time we have already lost the game. So with that said, let's also look at the constraints. First, n is bounded below by 1. So in other words, we have at least 1 monster. And then it's bounded above by 10 to the power 5. So 10 to the power 5 is a decent large number. So for such large number, we cannot use, say, n square time complexity algorithm, right? So the distance and the speed have elements in between 1 and 10 to the power 5. So with that said, basically we can look at the logic. So here I give the walkthrough for 3 examples. So the first one is a general example. So here I have a distance, this like this, and speed is 1, 1, 1, 1, and 4. So this is also a test case. So in this test case, we're going to return 3, right? So the reason is that overall we need to consider the arrival times, right? For this example, so because there are 3, 3, 3. So these 3 monsters will arrive at minute 3. So in other words, we have 3 at minute 3. We have 3 monsters arrive, and then for the last monster with distance 4, because it has a speed 4, so it will arrive at minute 1. So at minute 1, there will be 1 monster arrive. So for the first monster with a distance 4, it takes 4 minutes for it to arrive. So it arrives at minute 4, or it will arrive at minute 4. So the logic will be the following. So at the current time, t equals 0, right? So this time, so we can kill or eliminate the only monster who will arrive at minute 1, right? So we eliminate this one, and then time becomes 1, right? Then at current time 1, so then we are going to consider times 3. So at times 3, there will be 3 monsters to come, but because the difference of time is t is 1 and the arrival time is 3, so we could kill 2 of the 3, right? So the time will becomes 3. So in this case, so we will have killed monsters 3, right? And another monster will arrive at the same time, so the game ends. In other words, at time t, we killed or eliminated 3 monsters, and the game ends. So this 3 is also the return for this example. I guess this example is very representative. So this is the first one. Now, if you look at the first example, so you have 1, 3, 4. So the arrival time is at time 1, there will be 1 monster. And time 3, there will be 1 monster. And at time 4, there will be 1 monster. So at time 0, so we can eliminate the monster to arrive at time 1. So the result will increment by this 1, and t becomes 1. Then at time t equals 1, so we can eliminate the monster to arrive at next arrival time, that is 3, right? Then result becomes 2 by incrementing this 1, and t becomes 2. Then at time t equals 2, so we can eliminate the monster to arrive at time 4, right? So in this case, the result is 3, and t becomes 3. And then all the monsters are eliminated, so we return 3 for this example. So this is the more targeted analysis. So if you look at example 3, so here we have 3, 2, 4 and 5, 3, 2. So this example basically tells that we need to consider the ceiling operator when we compute the time to arrival. And for example, the distance is 3 and speed is 5. So time taken is 3/5, but we count 1 minute, right? For this in this context. So the arrival time will be the following. So the first 2 monsters will arrive at time 1, right? And the third monster will arrive at time 2. Therefore, at t equals 0, so we can kill 1 out of the 2 monsters to arrive. Then the result will be 1, and t will be 1. But another monster will have arrived, so we return the current result state, that is 1. So with that said, basically we know the logic. The logic will be following, right? So we count, we check arrival time from early to later, right? Or from small to large. In other words, we need to sort these arrival times, and then we check time and count how many monsters we can eliminate, right? So we're going to specify how we make this comparison, right? So with that said, I hope that you have digested the problem requirement. I guess it's always worthy of doing such a digest so that you can write code more clearly. So with that said, let's look at the coding part. So if you have grasped the logic, so writing the code is actually a breeze. So first, I want to get the arrival times. So I just call it times. Then basically for distance, let's call it s, and speed, let's call it v. So as in physics, right? So distance and speed. So here I'm using the zip function, right, to make tuples out of the two. And then I want to compute the arrival time. So that will be mass. So I'm going to use a ceil operation. So S over V, right? So while we use the ceiling operator, you can look at example 3, for example. So now we want to update this one. So times t. So we want to count how many monsters arrive at time t. So that is times get. So let's check if t is in the dictionary or not. If not, we set it to be 0. Then we count increment by 1. And then we want to sort the arrival times. So let's call it arrivals. So we sort it times keys, right? So this way we are going to sort the time from small to large. Then so our current time is t equals 0. Notice that at t equals 0, we can kill 1 at least, right? So the result will be the number of monsters we can eliminate. So now we just need to iterate over the arrival times. Let's call arrival in arrivals. So now let's see how many monsters will arrive at this time. So times arrival. So notice that current hour time is t, right? So if, for example, just at time t equals 3, you have 3 monsters to arrive. So that's okay, right? Because at t equals 0, you can kill 1. And t equals 2, you can kill 1. And t equals 3, you can kill 1, right? Actually, the number of monsters, so let's say we have a time, we have an n monsters. So the number of monsters, we can eliminate is, so you can do the counting, right? So t equals 0, and t equals 1, and t equals 2, up to 10 minus 1, right? So you count this will be 10 minus 1 minus 0 plus 1. That is 10 minus t anyway, because t is 0. So this is the monster we can kill. If the n monsters is larger than this count, then we will lose the game, right? So now with that digested, let's look at the counting. So can kill or can eliminate. So let me write eliminate. That is arrival time minus t. So actually this is computed by this t plus 1 up to arrival time minus 1. So it's arrival minus 1 minus t. Then you count this one itself. That is arrival plus t. Not plus t, minus t. Right? So this is the monsters we can eliminate, right? So if n monsters is larger and is less than the can eliminate, and then we can increment the result by n monsters. So we can kill all these monsters ahead of time. Then t becomes increment also by this amount, right? Because each minute we eliminate 1. So otherwise, so we just need to return result, the current state plus the monsters we can kill, right? That is, we can kill this amount. But the other monsters will arrive, right? We lose the game. That's why we return. So overall, we just need to return the result, right? So we don't care about directly return n like here. So as long as after this for loop, there's nothing returned, so we just return the result state. That result state will be the number of monsters given, or the length of the distance or speed. So with that said, I guess we're ready to do a test. Yeah, it passes one example. Now let's look at the generic case. Can kill is not defined, so here I think I use can eliminate. So now let's check that. Yeah, let's check again. Yeah, it passes all the cases. So that's basically about it for this problem. So let me give a quick summary. I guess for this kind of problem, because we need to count both the time and the arrival time and the number of monsters arrived at that time. So here we need to be clear that we digest the problem in certain precision. So as for time complexity, it's very easy to analyze. So for example, this part 4, and this is the O of n, right? And then in general, we do the sort. The sort is m log m algorithm. So here m is a number of different keys, right? But this m is bounded by the length of this disk. So this loop is O of n. Let me use big O. So this is also big O. Basically means up to a constant, right? So for this one, this for loop is also linear. So O of m. So it's the number of different keys, right? Then you can get the complexity easily. So with that said, I guess that's it for this video. Thank you.